AP Chemistry, we are starting a new unit called Intermolecular Forces, and the first lesson is called Intermolecular Forces, where we're going to learn of the 4 types of intermolecular forces. So let's review. There are 3 types of chemical bonds that we have talked about in this class. The one that we're going to deal with the least is that on the left side. Those are metallic bonds. Those are simply the bonds between metal atoms. They have very low ionization energies in their valence orbital, and they have a large number of orbitals usually, so those electrons can pass kind of somewhat freely between atoms. They jump around between atoms. So those are metallic bonds. In the middle is the first type of bond we learned about. Those are ionic bonds, and that is when an electron jumps from a metal to a non-metal. A strong guy takes the electron away from a weak guy, and the strong guy becomes an anion, negatively charged, and the weak guy, the metal, becomes a cation, positively charged, and the positive and negative charges attract each other, and they form structures called crystal lattice structures. Finally, there are covalent bonds. Those are the types of bonds in your body. We see that over on the right. Water molecules are covalently bonded. So what will happen is they will share electrons. They're between 2 nonmetals, and so it's 2 strong guys having a tug of war for electrons. Neither one wins, and so the electrons are shared. So when we talk about intermolecular forces, for the most part, we're talking about covalent bonds, and not ionic or metallic, although there could be a discussion in those areas. We're really going to focus on covalent bonds because they form independent structures called molecules. So only covalent bonds form separate structures called molecules. Remember, molecules can move around independently of each other, just like cars. So when you boil water, water molecules will go up into steam or vapor, and they can move apart from each other. So what intermolecular forces do, this is really the essence of this entire unit. Intermolecular forces determine whether molecules stick together or not. It's just that simple. A key point is that intermolecular forces, which we abbreviate IMF, are much weaker than covalent, ionic, or metallic bonds. So let's talk about the 3 states or phases of matter. First, we have solids, and we'll do it in context of water because that's the best way to understand it, something you're familiar with. So water in solid form retains its own shape, so those ice cubes will remain as cubes as long as they're frozen. They're incompressible. You can't squeeze those ice cubes down, and they do not flow. They'll just sit there like blocks. They might as well be iron blocks. They just sit there. In liquid form, the liquid takes the shape of the container. Liquid is interestingly also incompressible. So just like solids, you can't compress a liquid. Very little. It can be compressed slightly, but then so can solids. And what that means is it's because the molecules, in this case of water, are fairly tightly packed together. And so you cannot squeeze down water. And it diffuses slowly, meaning if you spill the glass, it'll kind of run away, but it won't spread out quickly. It takes the shape of the container, but it maintains a constant volume. If you took the water in that glass above and poured it into a very short, wide glass, it would have a different shape because the glass is shaped differently, but it would still be the same amount of water. It would still be the same volume. Take up the same space. If you were to measure the space it takes up, it would still be the same. Finally, there's gas. Again, the gas in the chemistry context has nothing to do with gasoline that people buy in a gas station. It simply means that the molecules have detached from each other and they can move around freely. Often they fly up into the atmosphere against gravity. Sometimes they don't. They will fall to the floor. To the surface, but they are separate from each other. That's a gas. They take the size and shape of the container. So, for example, let's say you have a bottle of strong perfume. It's in a bottle. So at that point, the molecules take on the size and shape of the bottle of perfume. if you take the top off the perfume or spray it, whatever you do to it, on a warm day, the scent of the perfume will spread throughout the room that you're in. So it will take on the size and the shape of the room. So gas takes on the size and shape of the container that's holding it. It flows and it diffuses in gas fairly rapidly. So that perfume would spread out probably within 5 minutes. You'd be able to smell it in different parts of the room. So that's solids, liquids, and gases. So intermolecular forces are a battle between kinetic energy and Coulombic attractions. So kinetic energy is caused by high temperature and assisted by low pressure, and it allows molecules to separate. The key to kinetic energy is it comes from the outside. It comes from outside of the molecules. Then what's trying to hold the molecules together is the Coulombic attractions. We've talked about that's simply the positive negative attraction that particles in chemistry or molecules have for each other. So when we talked about water molecules, we said they were polar, they had a positive end and a negative end, and so they would want to stick together. The amount of Coulombic attraction between water molecules is fixed. It's just whatever the structure of that molecule and the positive negative ends are. That's fixed by nature. So that's internal to the molecules. That's a function of the molecules and what molecules you're dealing with. Kinetic energy is a function of how hot the room is, or whether you have the water in a freezer or over a hot stove. So that's external. So these two things battle. If you have very low kinetic energy, then the Coulombic attractions will dominate, and the molecules, say water molecules for example, will stick together. If you put in some kinetic energy, maybe just at room temperature, the Coulombic attractions stay the same. They don't change, but now you've put more energy into the water molecules, so they start to wiggle more. They start to shake apart, and they move around each other. If finally you put the water over a stove, again, the Coulombic attractions between the water molecules are the same. That's fixed by the structure of water molecules. But the kinetic energy overwhelms the Coulombic attractions, and the water molecules can break apart and float off into the atmosphere as steam. So this is really the essence of what intermolecular forces are about. This battle between the Coulombic attractions of the molecules and the kinetic energy that's coming from the outside to shake them apart or to make them come apart. So generally, matter moves from liquid to gas to solid in two ways. First, it can be by reducing the temperature so that the molecules decrease energy and move closer together. So that's what we just talked about. If this goes from room temperature, these two water molecules, down to 0 degrees, which is freezing, the kinetic energy will be reduced and the Coulombic attractions will start to dominate. And that means that the two water molecules will stick together. Not exactly in the way you're seeing there, but that's good enough representation of it. Okay? Now, the other way you can get the water molecules to come together and stick together is just by brute force over on the right, by increasing the pressure. That's just by squeezing them together while keeping the temperature constant. And so you're squeezing the molecules together. So here you have a piston. It's going to push down on those molecules like that, and it's just going to squeeze them together. So either by reducing temperature or increasing pressure, that's a way you cause molecules to come together. If you did the opposite, it would allow them to come apart. If you increase the temperature, as we said earlier, like boiling water, or if you reduce the pressure that's on the molecules, it would make them better able to come apart from each other. So if the kinetic energy overwhelms the Coulombic attractions, then molecules separate and exist as gas vapor. So we saw this image when we were studying gas laws. They move about randomly and independently. They're not just changing direction for no reason. You can think of them as bumping into other vapor molecules or air molecules. If this is steam, it's vaporized water, then they could be bumping into air molecules. Also, heat flows coming up can cause them to change directions as well. Okay, if the kinetic energy and Coulombic attractions are about equal, then the molecules stick together but can move around each other. So these molecules represent what a liquid would be, what liquid water would be. They're free to move around each other, but they're still going to stick together. So this is kind of a middle ground of this battle between intermolecular forces and kinetic energy. There's enough kinetic energy to break them so that they don't stick in rigid positions. They're not stuck in one place, but there's not enough kinetic energy to allow them to break apart from each other. So this is kind of the middle position here. If kinetic energy is low compared to the intermolecular forces, then the molecules will stick together in fixed places. This produces a solid. Now, nothing in the universe stands still. So even in a solid, even in ice, even in iron, a piece of metal, the molecules are wiggling like this. If you put more heat into them, they'll wiggle faster. But everything in the universe moves. And so these molecules, this is actually not water, it's another substance, but it doesn't matter, are wiggling. So hydrogen sulfide, H2S, has a freezing temperature of negative 82 degrees centigrade. Even the molecules in a solid move. So everything has kinetic energy. So we're going to study now the 4 different types of intermolecular forces. Okay, the first we're going to talk about are called ion dipole forces. So table salt consists of sodium ions and chloride ions, NaCl, arranged in lattice structure like bricks in a wall. So we talked about that when we talked about ionic bonds. Water is a polar molecule with the negative dipole pointing toward the oxygen atom. So think of a water molecule. The electrons are pulled over toward the oxygen in a water molecule because that's more electronegative than the 2 hydrogens that are in the water molecule. So the electrons get pulled toward the oxygen atom in a water molecule. That means that the oxygen side of a water molecule is more negative and the hydrogen side is more positive. So go back and review the fundamentals lessons, and that's in the lesson on covalent bonds. It talks about polar covalent bonds. So the negative oxygen side of several water molecules point towards the sodium. So remember, those are ions inside of that salt crystal there. Sodium is the positive, that's the blue, and that's the cation. And the chlorine, that's the green, that's the negative, that's the anion. So study those water molecules surrounding those sodium ions and chloride ions. The positive side of several water molecules will gang up on a chloride ion. The chloride ion is negative. So the positive side, the hydrogen side of several water molecules, it's not just one, it has to be about 4 or 5, will gang up on one of the chloride ions and pull it away from that salt crystal. So this is how salt dissolves. So you see there, right next to the salt crystal is a chloride ion by itself, and it's surrounded by the positive side of 3 water molecules. Now, if you look at the sodium, the positive cation up at the top there, you see 2 water molecules surrounding it. That's the negative end of the water molecules. The oxygen side, that's the red side of the water molecules, is pointing towards the positive sodium ion. So what happens is they gang up on a sodium ion over in that salt crystal and pull it away. So the positive end of water molecules pull the chloride ions, the negative chloride ions away, and the positive end or the negative end of several water molecules pull the positive sodium ions away, and that's how salt dissolves. So salt is NaCl. We've talked about that before, but it doesn't break apart as NaCl. It's not like a molecule. It breaks apart in its ionic form. Sodium ions, Na+, and Cl ions, Cl-. Okay, so that's what you're seeing here. So that's what that arrow is pointing to. It's pointing to the negative oxygen side of several water molecules pointing towards an Na+ ion. The positive hydrogen side of several water molecules point toward the Cl- ion. So these are called ion dipole forces. Why? Because the sodium chloride is made up of ions. Those are completely +1, -1 charges. Sodium is +1, chloride is -1. The water molecules are not +1, -1. We said they're polar molecules. They have a positive side and a negative side, a more positive and more negative side. So they're dipoles. They're called dipoles. That means they have two poles, a positive and negative side. So this is an example of an interaction of an intermolecular force between dipoles, those are the water molecules, and ions, those would be the sodium or the chloride ions. That's called an ion dipole force. So both of these effects are called ion dipole forces. Dipole-dipole forces attract polar covalent molecules to each other. So here we have a couple of hydrochloric acid or HCl molecules, and polar covalent bonds have a positive side and a negative side. Now that little symbol is called delta, so delta plus indicates the positive side of a polar molecule, polar covalent molecule, and the delta minus represents the negative side. The point here is that the positive and negative sides of polar covalent molecules are not a full 1+ or 1- the way ions are. Ions are a full 1+ charge in the previous slide. In the case of sodium, it's 1+ for sodium and 1- for chloride. Here it's something less than 1. The hydrogen side is a little bit more positive, but not quite a full +1. The chloride side is more negative, but not a full -1. But what you see there is they do have a positive negative side, and so the positive side of one dipole molecule will be attracted to the negative side of another dipole molecule. They don't have to be the same substance. In this case they are, but they don't have to be. So that's called a dipole-dipole force. So hydrochloric acid is polar because a highly polar chloride ion pulls the hydrogen electron towards it. It doesn't totally take it away. That would make it an ionic bond. It just pulls it more closer to the chloride ion. Below, the positive hydrogen side of an HCl molecule is attracted to the negative chloride side of another HCl molecule. Now we go on to the third type of intermolecular forces. These are called London dispersion forces, named after a scientist, not after the city of London. So London dispersion forces are temporary changes in the polarity of a molecule due to the random movement of electrons. Dispersion forces are how nonpolar molecules attract each other. So we mentioned some time ago that polar molecules attract polar molecules like we saw in the last slide with hydrochloric acid. That makes sense. They have a positive end, they have a negative end. The positive end is attracted to the negative end. However, nonpolar molecules, you might ask, how do they get attracted to each other? They don't have a positive negative end. They're not like little magnets. Well, the answer to that question is London dispersion forces are what allow nonpolar molecules to be attracted to each other. So here we have atoms. It's just a very simple atom. It could be hydrogen. And the electrons are circling. So you have a proton and an electron in each. And what happens is when the electron in atom number 1 is to the right side of its nucleus, the proton, then what it does is it creates a negative side, temporary negative side to that particular atom, to atom number 1. Having that electron over there on the right side of atom number 1 pushes the electron in atom number 2 also over to the right side of atom number 2. And so that does two things. It pushes the electron away, and then the electron in atom number 1 has a very weak attraction to the proton, that's the nucleus, in atom number 2. So there's a weak delta negative, delta positive attraction between those. And it's temporary. Why is it temporary? Because electrons can move around. They don't just stay in one place. But it can have that temporary effect. Similarly, the electron in atom number 2 is over on the right side of that atom, so it's going to push the electron in atom number 3. It's going to repel it and push it over to the right side of atom number 3, and the electron in atom number 2 will then have an attraction to the proton, to the nucleus of atom number 3. So again, these are temporary and very weak intermolecular forces that are caused by just the temporary location of electrons. So when the electron in the hydrogen atom on the left moves to the right side, that's atom number 1, it pushes the second atom's electron to the right, that's atom number 2. If this effect repeats throughout many atoms, it creates a temporary polarity that attracts the atoms to each other. So now you have a bunch of atoms with weak but nonetheless positive and negative sides that are attracted to each other. The strength of London dispersion forces is a function of how many atoms you're dealing with. If you're dealing with large numbers of atoms, this effect can actually become fairly strong, even though London dispersion forces are considered the weakest of the intermolecular forces. If you have enough atoms, they will cause a fairly strong intermolecular attraction. London dispersion forces, abbreviated LDF, are small but can produce a stronger attraction between large molecules with many electrons. So let's look at some nonpolar. Most hydrocarbons, in fact all hydrocarbons, are nonpolar. So let's look at a gas. CH4, that's methane molecule, is very small. It has weak London dispersion forces because it has only 10 electrons. You can count that. It's CH4. The carbon has 6 electrons, and each hydrogen has 4 electrons. Or excuse me, the hydrogens all together, all 4 have 4 electrons. That's a total of 10 electrons. So methane has very weak London dispersion forces, and so methane molecules are not attracted to other methane molecules, and that's why methane, natural gas, is a gas. They come apart from each other because they don't have strong attractions to each other. Now let's look at a little bit bigger hydrocarbon. And hydrocarbons only have a carbon and a hydrogen. So this is octane. It's a form of gasoline that people put in their car. It's C8H18. So if you count the number of electrons in 8 carbons and in 18 hydrogens, you'll see that it has 66 electrons. This is strong enough to make octane a liquid with other octane molecules. So they tend to stick together but not real tightly so they can flow around each other, and that's why the gasoline that people put in their car at the gas station is a liquid. So they'll stick together but not really firmly, not real firmly. Finally, let's look at a very large hydrocarbon. So this is called paraffin, and it's candle wax, and it has the formula C40H82. And if you count up all the electrons in that many carbons and that many hydrogens, you have 322 electrons. This many electrons, all pushed over to one side of the molecule, form strong enough attractions to make paraffin a solid at room temperature. So as you know, candle wax is a solid at room temperature, although it can melt fairly easily if you light a match to it. One that's even bigger is what they pave streets with. It's called asphalt. That's a hydrocarbon with very, very large molecules, much larger than paraffin. And as you know, the asphalt that paves streets is very solid. So London dispersion forces, if you have large enough molecules with enough electrons, all of them getting pushed over to one side, that creates some fairly strong bonds if and only if it's a large molecule. And so that is how London dispersion forces hold nonpolar molecules together. The shape affects the strength of London dispersion forces. Longer, flatter hydrocarbons, such as N-pentane on the left, form stronger London dispersion forces than round neopentane molecules because they fit together tighter with less space between them. So this is just kind of intuitive. You can see how the molecules on the left will fit more tightly together, and therefore these relatively weak forces will be able to latch on, will have one molecule latch on to the other more easily. Whereas the round ones, the ones on the right, they don't fit together quite as well, so the weak London dispersion forces can't really reach across those big gaps in between those molecules on the right, and so they don't really have as strong a London dispersion force. So the point is, the shape of the molecule can affect the strength of the London dispersion force. Now we get into hydrogen bonds. These are the strongest of the London dispersion forces. And in this class, I call them hydrogen bond forces. They really shouldn't be called bonds. They are not chemical bonds like metallic, ionic, and covalent. They're intermolecular forces and should be called intermolecular forces. So although every book calls them hydrogen bonds, that's just what they're called. We'll call them hydrogen bond forces to keep it clear that they're not like a covalent, ionic, or metallic bond. Again, chemical bonds are between atoms. Intermolecular forces are between molecules, groups of atoms, and what makes them want to stick together. Hydrogen bonds occur when a hydrogen atom is bonded to three of the most electronegative second row elements: nitrogen, oxygen, and fluorine. It is only when nitrogen, oxygen, or fluorine are the central bonds in a molecule can you have hydrogen bonds. Therefore, they're fairly rare. They don't happen all that often. So let's look at what happens. When oxygen pulls the electrons of hydrogen toward it, an exposed hydrogen nucleus, a proton, is left exposed. So let's analyze what that means. Take the water molecule on the top. Let's just focus on that. Remember, it's polar. The oxygen is more electronegative than the hydrogen. So the electrons, all of them, tend to get pulled toward the oxygen. And what that does is it leaves the nucleus of the hydrogen, which is just a single proton, kind of sticking out, kind of exposed, because the electrons are being pulled away from it. So what that means is those positive charges sticking out, those nuclei of the hydrogen atoms, can be attracted to the lone pair electrons of another water molecule, such as the two down below. So let me continue to read. This proton is attached to the lone pair of another molecule with a nitrogen, oxygen, or fluorine atom as the central atom. In this case, all three of the atoms that you see there, or all three of the molecules, have oxygen as the central atom. The hydrogen atom has a fairly strong attraction to the other atom, though it is not nearly strong as its own covalent bond. So if you look at the proton, one of the protons in that upper water molecule there, the one on top, it does have an attraction. Each of those protons has an attraction to another molecule, but it's not going to get pulled away from its own molecule by one of those other molecules. So it's covalently bonded to its own molecule. That's a really strong bond, but it has a hydrogen bond attraction to the lone pair of a different water molecule. So although hydrogen bond forces are the strongest of the intermolecular forces, they're still much weaker than an actual covalent bond, which is bonding those protons and those hydrogen atoms to their own oxygen. So let's look at some. You can mix and match these. Now, why is it that hydrogen, it's only oxygen, nitrogen, and fluorine? Because they're three of the most electronegative elements on the periodic table. So they pull the electrons away from the hydrogens, and that exposes the protons. Other elements, such as carbon, are not electronegative enough to pull the electrons away from the hydrogen atom, so the protons in a CH bond are not exposed. The proton, which is the nucleus of the hydrogen, in a CH bond does not stick out. It's not as exposed as it would be with oxygen, nitrogen, and fluorine. So for a hydrogen bond to occur, okay, and you need to learn this, you need to memorize this, a hydrogen atom must be attached to a nitrogen, oxygen, or fluorine. So here you see that the two molecules on the left are water molecules, H2O. So they're attached to oxygen. The one on the lower right is a nitrogen. It's an ammonia molecule. It's 3 hydrogen atoms attached to a nitrogen. And the one on the upper right is a hydrofluoric acid. It's 1 hydrogen attached to a fluorine. So let me start the reading again. For a hydrogen bond to occur, a hydrogen atom must be attached to a nitrogen, oxygen, or fluorine, and it must be attracted to the lone pair of another nitrogen, oxygen, or fluorine. So you need to memorize that sentence, okay? That's got to be really clear what is and what is not a hydrogen bond. So we have kind of a mix and match here that we'll look at. So here, a hydrogen atom on a water molecule hydrogen bonds with the lone pair on a nitrogen atom. So in other words, a water molecule which has a central atom of oxygen can hydrogen bond with an ammonia molecule which has a central atom of nitrogen. So that's okay. You can mix and match, in other words. Here, a hydrogen atom on the nitrogen, that's the one on the lower right. Here, a hydrogen atom on a nitrogen atom hydrogen bonds with the lone pair on a fluorine atom. So you can see how the proton, that's the nucleus of a hydrogen, on the ammonia molecule, that's the nitrogen, the NH3 there, will be attracted to the lone pair on a fluorine. So in other words, it's got to be oxygen, nitrogen, or fluorine, hydrogen bonding with nitrogen, oxygen, or fluorine. Okay, those are the only elements that can be the central atoms for hydrogen bonds. And that makes hydrogen bonds fairly unique. Not any atom can do it, only those 3. Hydrogen bonding works because nitrogen, oxygen, and fluorine pull the electrons away from the hydrogen so completely that an exposed proton, you can think of those white plus signs as being exposed, they're kind of just sticking out there, that an exposed proton is left sticking out from the molecule. The hydrogen bonds of water, H2O, are stronger than the hydrogen bonds of ammonia, NH3, or hydrofluoric acid, HF. There is 1 hydrogen on a water molecule for each lone pair on another water molecule. And that's a perfect match. So hydrogen bonds of water are going to be stronger than hydrogen bonds of ammonia or hydrofluoric acid because it's a perfect 2-to-2 match. You have 2 protons, positive charges, that can be attracted to the 2 lone pairs. Now, I got to point out, this is not a possible situation here. 1 water molecule, the 2 hydrogens on 1 water molecule will not attach to the lone pairs on another single water molecule. What you see in that picture will never happen. It will be one of the hydrogen atoms, one of the hydrogen protons there will attach to the lone pair on 1 water molecule, and the other one will attach to the lone pair on a different water molecule, a third water molecule. You can't have them match up. The reason I drew it like this was just to illustrate that there's a 2-to-2 matchup here. 2 protons for 2 lone pairs on water molecules. So everyone has a dance partner. You go to a dance and there's 50 boys and there's 50 girls and everybody has a dance partner. So there's just as many protons on a water molecule as there are lone pairs. They match up perfectly. Ammonia has only 1 lone pair for every 3 hydrogens, protons. So look at that. There's ammonia. It's NH3. So it has 3, they look like X's, but they're supposed to be pluses for the hydrogen. So they have 3 positive charges, but each one only has 1 lone pair. So it's like you go to a dance and there's 3 times as many boys as girls, then a lot of the boys won't have a dance partner. Okay? So you have more of those plus signs, those white plus signs, the protons, then you do lone pairs. If we go over in the other direction to the fluorine, so there you see no lone pair to bond with for those two protons. If you go over to the fluorine, hydrofluoric acid has only one hydrogen proton for every 3 lone pairs. So you're at the dance and there's 3 times as many girls as boys, then not every girl has a dance partner. Okay, so there's not a perfect one-to-one match like there is with a water molecule, where you have exactly 2 protons and exactly 2 lone pairs and everything matches up properly. So no hydrogen to bond with for those 2 lone pairs. So water hydrogen bonds most efficiently and has the strongest hydrogen bond. So that's going to be an AP level question. Why are the hydrogen bonds in water stronger than the hydrogen bonds in ammonia or hydrofluoric acid? It's because they have the same number of plus charges as lone pairs, so they match up perfectly, and so they can produce stronger bonds. So comparing intermolecular forces. Generally, the following is the order of strength of different intermolecular forces from weakest to strongest. London dispersion forces are the weakest because they consist of temporary dipoles, and they really are only important in nonpolar molecules. All molecules have London dispersion forces, but in polar molecules and dipole, and ion dipole, and hydrogen bonding molecules, they tend to be overwhelmed by those other intermolecular forces. It's only really in nonpolar molecules that we talk about London dispersion forces. Dipole forces are next because they consist of the positive, negative ends of electrically neutral molecules such as water. So water has a sort of negative end and a sort of positive end, and they sort of stick together in what's called a dipole force. Ion dipole forces are stronger than dipole because they contain a fully charged ion. Remember, an ion is fully charged as a +1 or a -1. It's not just sort of positive and sort of negative the way a water molecule is. So you have a fully charged +1, -1, or -1 ion. But the water molecule or the dipole molecule, could be water, could be something else that's polar, will attract to it. So ion dipole forces are stronger because they contain a fully charged ion with the end of a molecule of the opposite charge. So go back and review the water causing the salt crystal to dissolve. And then finally, hydrogen bond forces are the strongest. Hydrogen bonds formed by water molecules being stronger than other hydrogen bonds. So their water molecule hydrogen bonds are stronger than those formed by ammonia or hydrofluoric acid. All right, so that finishes our lesson on the 4 types of intermolecular forces. This is pretty heavily tested on the AP exam, and it's not that hard to understand. So review this video several times if you need to, and know how to describe each of these types of intermolecular forces. We'll have 2 more lessons in this unit, and then we'll move on. So we'll see you on the next lesson.